Thank you for catching the fact that I wasn't recording. Don't want to make that mistake 2 times in a row. All right. Okay, so this one's SP2, so it is completely conjugated. Now we have to figure out the 4th criterion, all right, and this has to do with the Huckel number of electrons. All right, what can you tell me about what's going on over here?
There's 4 pi electrons.
It's 4 pi electrons, 2, 4, nothing contributing from there, okay? So which formula is that going to give us a whole number? 4n, yeah, 4n equals 4, n equals 1. So how would you classify this ion? This is an example of an anti-aromatic species. Okay. Does that make sense? Yeah, and you're starting to see a pattern here from this stuff and then the stuff we went over the other day. In large part, it's about figuring out, the hybridization status of sort of this intervening atom here. The one that sort of looks a little bit different than the rest, but doesn't necessarily have a double bond attached to it. And then seeing if it has extra electrons and seeing where they go. We can look at a very similar one. But this time with a negative charge. And this one can be a little bit trickier. Okay. What's the hybridization of that carbon? What's that? SP3. Question mark. Looks like it, doesn't it? It does have another hydrogen out here. You have 3 bonded atoms, so that's 3 groups, and then you have an unshared pair. But so that's 4. That corresponds to SP3. However, there's a little caveat with this one. What's that? It is an allylic carbanion. Yeah. It's just like you saw with the heteroatoms, right? You saw with heteroatoms, like a nitrogen or oxygen, if you had a heteroatom in the allyl position and you had unshared electron pairs, what could you do? You could draw resonance structures. Guess what? You can do the same thing here. Right? A pair of electrons could hop over here, form a double bond. This pair of electrons could hop over here to give you a negative charge at that carbon. And there's others that we could draw as well, but I'm going to just stop with this one for the moment. In this position, that carbon only has 3 groups, so it's sp2. So we would say that carbon has partial what? What catchy little phrase did I use the other day? Partial double bond. There you go. Partial double bond character. So it's got to be ready at a moment's notice to resonate and adopt that hybridization status. So you can add this to your list of exceptions. If you have an allyl carbanion, it's going to be sp2. So you're going to have 3 hybrid orbitals and 1 available p orbital. So yes, that one is completely conjugated. Now we got to figure out where these electrons go, right? I've drawn them by default on the outside. Excuse me. We got to figure out if they actually stay there or go on the inside. All right. What can you tell me about the current allocation of electrons it's got? How many of its hybrid orbitals are currently used? What's that? Two? Which two? Where? Right. If you look at this, remember, what type of electrons go in hybrid orbitals? Sigma or pi? Sigma. So ask yourself, how many sigma bonds is this carbon currently making? 3. Here, here, and here, right? 3 sigma bonds, 6 sigma electrons. So how many of these hybrid orbitals are already occupied? What's that? All of them. Yeah. So you don't have any available. Does that carbon currently have any pi bonds? No. So where are those unshared pairs going to end up being? Only thing left over is a p orbital, so they're going to go in there. And if they're in the p orbital, that means they got to be on the inside. All right. If they're on the inside, how many total pi electrons do we use for our Huckel calculation? 6. 4n plus 2 equals 6. N equals 1. And we can determine that it is aromatic. Excuse me. So you see the process is very similar to the one that we use for heteroatoms, right? It just looks a little bit different. All right, speaking problems this morning. Are there any questions about how we got that one? All right, let's do another series here. And please bear with me on this, because for this set, I'm actually using a 7-membered ring, which I am terrible at drawing. Really, seriously. After you just get used to drawing pentagons and hexagons so much, drawing a heptagon is really, really unnatural, and it's harder than you think. So bear with me. All right. Three, four, five. Bless you. So like that one has an abnormally long looking bond on the end. But you know what? I'm going to keep it there because that's actually one of my better ones. All right. So let's say we had this. Just like with last time. We can look at a few different charged states of it. What's going to be the status of this one? Aromatic, anti, or non? Non, right? Yeah, this one's pretty easy. Again, you know it's not completely conjugated because that little guy right over there has sp3 hybridization. That was a pretty good one, except it looks like it's been squished. Well, let's look at the carbocation and the carbanion, respectively. All right, based off of the example we did last time, take a look at that for a minute or so and see if you can figure out aromatic, anti, or non. See in the class today, takes me back to my Arkansas days. I worked at a smaller college back then, so like my max in OChem was usually like 15 people. I know, right? Yeah. If you have an idea on this one, let me know. It's also a lot easier when it's a smaller class for me to just stare at you and make you uncomfortable until you say something. There you go. Yeah, aromatic. Very good. This one's aromatic because, we have an allyl carbocation, so we know it's sp2 hybridized. Right? We have one H over there. All right, 3 groups around it. All right. We actually don't have any electrons here to place, so everything's where it should be. We have 2, 4, 6 electrons, pi electrons. As we've seen many times, that corresponds to the Huckel number for aromaticity. Okay? Does that make sense? Let's try this one. All right, let's try the carbanion. Think you got it? Let me know. This one is anti-aromatic. I'm sure many students out there probably observed the fact that, hey, by process of elimination, he's shown a non and an aromatic one. He's probably going to do an anti. But how did you figure that out chemically or at an electronic level? Yeah. Yeah, you're both right. Yeah, again, we have sp2 hybridization here because it's an allyl carbanion. This time, we have to place a pair of electrons either inside or outside of the ring. Don't forget the H, it's still sitting there. All 3 of your hybrid orbitals are taken up with these 3 sigma bonds. So that means those electrons have to go in the ring. It means you have 8 pi electrons, which corresponds to the Huckel formula for anti-aromaticity. Very, very good. Are there any questions on how we got any of those 3 examples? Yeah, you see, it's a very, very formulaic process. Once you get it down, it's pretty simple. You can even, have charged heterocycles as well, right? We could take, let me Or we could have something like this. Right, that oxygen has 3 bonds, so as we've seen before, oxygen with 3 bonds has a positive charge. It's also got a pair of electrons sitting here, so we can approach this in the exact same way, though, that we've approached the other problems. All right, work on it for a minute and see if you can tell me what it is. And I'll work it in my head. If you come up with something, please share. Just so you know, if you volunteer and answer now, it's a little different because you have people in here, but you also kind of have the thought it's being beamed into cyberspace too with Zoom. Even though, psychologically it's still the same people, but they can't see your face either. So. All right, I see some people who aren't working anymore, so I'm betting you guys have an answer. Any volunteers to share their answer? You got a 33% chance, right? 1 in 3. Can't beat those ones.
Aromatic.
Aromatic? Ding, ding, we have a winner. Yes, it is indeed aromatic. Yeah, absolutely. Again, you approach this one just the same way you've approached any of the other ones the last couple of days, right? Everything's pretty obvious as far as these carbons. The question is, okay, what's going to be going on with that oxygen, right? Well, that oxygen has 1, 2, 3 groups around it, right? So it's going to be sp2 hybridized. So it's going to have 3 hybrid orbitals and 1p orbital, completely conjugated. Then you just have to figure out where the unshared pair of electrons goes. All right. How many how many hybrid orbitals are taken up currently? 2. Yeah. Sigma bond here, sigma bond here. So you got 1 left over. How many p orbitals are already taken up? You have 1 pi bond. So that p orbital is occupied. That means the electrons have to go in the hybrid orbital, which means they stay on the outside. And since they stay on the outside, that means you have 2, 4, 6 pi electrons, which corresponds to the aromatic Huckel equation. that make sense? Are there any questions about how we determine the aromaticity of that compound? Fun fact, by the way. Huckel is actually technically not pronounced Huckel. It's German. It's actually pronounced Hickel. But like every single organic student ever always says Huckel. So I've given up over the years trying to correct that. But, you know, should you be having a casual conversation someday with somebody about, you know, this guy, which I'm sure you will, his name is Hickel. All right. All right, so there's really one more major topic in this chapter. And what I'm going to do is scoot into camera range here while I'm talking. I alluded the other day to something called molecular orbital theory. And that's really the basis for why, you know, aromatic compounds are extra stable, anti-aromatics are extra unstable. It's basically another orbital bonding theory, right? Or sort of like the hybrid orbitals, sp3, sp2, sp. That's called atomic orbital theory. Molecular orbital theory is fairly complex. And it has to do with the formation of certain types of orbitals called bonding orbitals and anti-bonding orbitals. I am going to give you a very, very, very light instructional tutorial on some of this. If you ever want to go into it much more in depth, Andy will take you through it in PChem for the 3 of you or so that end up taking PChem. PChem is usually a really small class. So, anywho, I'm going to use benzene as a model. Right? And we've seen that in benzene, you know, we said it's completely conjugated. It's got 6 p orbitals, 1 on each carbon. That overlap with each other. All right. Okay, so let's take a look at these orbitals. Why don't just draw 2 of them as represented? Let's say we had a couple of these p orbitals sitting right here. All right, each one of these orbitals has a couple of lobes, right? Looks like a little figure 8. All right, according to molecular orbital theory, these lobes are not the same. I'm just going to shade one of them to make it look different. One of the lobes is referred to as a, actually, no, never mind. I'm not going to get to that yet. Just know that the lobes just know that the lobes are different from each other. We're just going to keep it simple. Right? So let's say you have 2 of these, right? And they happen to be lined up like this. That's a favorable bonding situation because like regions are lined up with each other. And in that state, you can get optimal overlap. However, you could also have something like this, right? Where like regions are not lined up with each other. In this case, because they don't line up with each other, they don't overlap. They don't share. You have to have like regions the same. All right? Now, whenever you have 6 of these in a species, like in benzene, there's several different combinations that you can have. Okay? With benzene, there's actually 6 different types of orbitals that can be made through various combinations of these p orbitals, right? When I say 6 orbitals, I mean 6 molecular orbitals is what we call them. And I'm going to represent each one of these orbitals with a little line. And there's a little dotted line, little imaginary dotted line that you can envision dividing these. The lower energy orbitals are all called bonding orbitals. The higher energy orbitals are called anti-bonding orbitals. And occasionally you even have some that fall exactly on this line, not in this example, but occasionally. If you had an orbital that fell on that line, that would be referred to as a non-bonding orbital. Okay? So y'all remember back from Gen Chem, basic orbital rules. Whenever you fill in electrons into an orbital, which orbitals get filled first? Higher energy or lower energy? Lower energy, right? So if you think about benzene, it's got 6 pi electrons, right? So we're going to fill them like this. That's what the molecular orbital diagram for benzene looks like. Right? And this is especially good because you see in this case, all of your bonding orbitals are completely filled. All of your anti-bonding orbitals are completely unfilled. Right? In fact, there's a couple of terms that we can look at here. These orbitals up here, right? Those are the highest energy orbitals that are completely filled. Stands for highest occupied molecular orbital, or HOMO. These over here, those are the lowest energy molecular orbitals that are completely unoccupied. That's called LUMO. All right. If your HOMO orbitals are completely filled and they're in the bonding region, that's good for stability. If your LUMO orbitals are in the anti-bonding region and they're completely unfilled, that's good for stability. It's when you get electrons starting to creep up here that causes instability. Also, if these orbitals right here, your HOMOs are not completely filled, that can add to instability. All right? So if you have an aromatic species, your molecular orbital diagram should look something similar to this, where the orbitals just below this dividing line are completely filled, the ones above it are completely empty. Okay? Y'all hanging in there? Any questions so far? All right. Like I said, I'm only doing a very light discussion of this. If you want more, you can take PChem. But I'm about to show you sort of a shortcut method for learning how to draw these molecular orbitals and predicting where the electrons are going to be. This can also give you an indication of yay or nay, is the molecule aromatic or not? All right. Now, there's a couple of different ways to tell whether a molecule is aromatic. One way is the way I've been teaching you the last 2 days, right? By drawing the structure, looking to see which atomic orbitals are occupied, blah, blah, blah. This is another way of doing it. And honestly, I think this is the inferior way. It's by doing something called the inscribed polygon method, also known as frost circles. And the reason I think this one's inferior is because it doesn't actually tell you whether it's anti-aromatic or non-aromatic. It just tells you yay or nay, it's aromatic or not. It doesn't distinguish between the other two. So I don't think it's as specific. However, you do see this pop up quite a bit on MCATs and DATs and stuff like that, so I really should go over. All right. Drawing a frost circle is really simple. All right, so what you do is you take whatever you're looking at. Let's say we went back to look at this guy. Right, we looked at that just a few minutes ago. All right, so there's a few steps. All right, first of all is to take your polygon, whatever this is a pentagon, and draw it so that one of its points is pointed completely down. Like that. So basically I took this one and turned it upside down. The next step is stupid. I really see no basis for this, but in the official rules for drawing frost circles, they say you're supposed to draw a circle around it that connects all the vertices. This has no practical application that I've been able to find over the years. It just makes it look more mystical and, you know, Halloween-y, I think, yeah, like you're drawing a pentagram or something. But I'm going to draw it just because that's what the rules say. All right. Then at each corner, draw a line. These lines are going to represent your molecular orbitals. And then halfway in between, you can draw the imaginary dotted line. So for this particular compound, we have 3 bonding orbitals and 2 anti-bonding orbitals. Okay? And then what you do is you take your pi electrons and you fill the orbitals. How many pi electrons do we have in this one? We got 6, yeah. Yeah, very good. So you take your 6, 1, 2, 3, 4, 5, 6. Your homos are completely filled. Your lumos are completely empty. So we would classify this one as aromatic. You could do the same thing if we changed it to the carbocation. What's the only difference with the carbocation? In this case, we only have 4 electrons to place. So you go 1, 2, 3, 4. Now in this one's our lumos are completely empty, but are our homos completely filled? No. This one, by looking at the frost circle, you can just say this is not an aromatic molecule. And I'm writing it like this specifically. I don't want to use the phrase non-aromatic because, like I said, you can't really distinguish between non-aromatic and anti-aromatic for this method. I think we said this one was actually anti, didn't we? Yeah. But you can't tell that through this. You can just say, yay or nay, it's aromatic or not. But this will work for, you know, that particular purpose for any one of these species. Even if you have heteroatoms. And I think we did this one the other day. But if you want to do a frost circle for it. Again, same thing, just draw the polygon. You don't have to draw the O's, just draw the polygon. Draw your stupid little circle. I'm sure the people who came up with this would probably not be very happy with me saying that, but whatever, right? Draw your orbitals. And then you fill in your pi electrons. How many would we draw here? How many pi electrons would we use? Y'all remember this one? We actually did this one the other day. If you go back and do our analysis, you'd find that each one of those oxygens has one pair inside and one pair outside. How many electrons are we placing? We're placing 8. So in this case, this is an example where we actually start putting electrons in the anti-bonding orbitals. So in this case, you can tell that this is not an aromatic compound, but for a different reason. Yeah. Does that make sense? Any questions about drawing frost circles? Like I said, they're super easy to draw. I just don't think they're as practically useful as the other analysis we did, but it's good to know how to do it. All right, that is the end of this chapter. Yeah, like I said, this is a pretty short chapter. So your test will cover the radicals chapter, conjugation, resonance, and dienes, and then introduction to aromaticity. So if you have an older edition, that's 15, 16, and 17. If you have the new edition, I think it's 13, 14, 15. Any questions about this chapter? Got you some sampling, I got you some practice problems. We have a few minutes. We could delve into the next chapter. But you probably don't want to do that, do you? I don't either. It would be really unproductive. I can almost guarantee you would remember nothing about it by the time you got back, and I think you realize that too. So I will let you have the next 8 minutes of your life to do whatever you want. All right? Have a good spring break, get some rest, do some organic chemistry, have some fun. But really, if you're doing organic chemistry, you're already having fun. So, I mean, you kill 2 birds with 1 stone. All right, have a good one.